Hi all, my name is Karen and today I'm going to be introducing you to hash tables. We're going to start with a hash table called chained hash tables, and a bit later on we'll move to a different kind called open addressed. So I know Chi has already spoken to you about arrays and what I'm going to call vectors. The Java terminology is sometimes vectors and sometimes it's array lists, and I don't really know what Chi's used, so I'll explain what I mean by both terms. For me, an array is something that's defined and it's fixed in length. So you say, I want an array of size 10 and it's only ever going to store at most 10 objects. A vector is very similar. It's indexed in the same way as an array, but it's of variable length. So you can say, I want one of size 10, and then later on, if you want to put 11th object in, you just push it in. So they're a lot more flexible and they allow you a lot more flexibility in your programming. There's actually two libraries for this in Java. One is the arrays lists library and the other is the vector library. You've probably used the arrays lists library. When I'm talking, I'm going to use the word vector just because it's really different to arrays and it just makes it clear what I'm talking about, something different. So arrays, fixed size, vectors, variable size. Got it? Both have reasonably low memory usage. Both allow random access, unlike linked lists, so you can say, tell me what's at array item 3, and it will tell you index 3, or vector index 3, and just get that back very quickly, so you get random access. They're both quite inefficient at removing or inserting elements other than at the end. So that's sort of the internals and how Java works, but you can trust me if you like, or you can go and look it up. If you actually want to remove an element from an array or a vector, or you want to insert an element at some place that's not the very end of the data structure, then that is actually really quite inefficient. However, what about finding an element? So if I want to find out if 6 is in this array, okay, in the top array, it's going to be pretty quick. Imagine that I loop around the array from index 1, and there it is. 6 is the very first element. I found it, bingo. Best case scenario, great. What happens in the second array we've got here? Well, I try index 1 and that's 4, try index 2 and that's 3, try index 3 and that's 2, 4 is 1, index 5 is actually 5, and finally index 6 is 6. I've had to look through 6 different elements to find that 6 number. So that's really quite slow. The worst case scenario, I'd have to look through the whole vector and then only find it at the very last element, or in fact even find it's not there in the very last element when I find out it's not there. So this is a real problem with using data structures like linked lists, arrays, vectors, anything that make you go through every element in turn when you're searching for something. Can we do vector? Well, you'll be glad to know, yes we can, and this is where hash tables come in. So a hash table consists of an array or a vector in which data, which is often called the key, is indexed using a special index. So we don't just say arbitrarily we're going to shove this data into position 1 in an array. We decide which bit of the array is going to go into really carefully. The idea is to establish a mapping between the set of all possible indexes, so all the possible places we could put something within the array or the vector, and all the possible data or keys we could want to store. That mapping is called a hash function and is really the beating heart of hash tables. So a hash function accepts a key, or value to be stored, and returns an index. Okay, keys vary in type. They can be any sort of data you want to store. So they could be strings, they can be a combination of things. For example, it could be a student ID, student's name, and student's date of birth. That'd be the sort of thing you might want to store someplace. But the index is always an integer. It tells you where you're going to put it in your vector. A simple example. So what I'd like you to do is store the numbers 14, 13, 16, 28, and 39 in a hash table. The hash table is an array of length 10, indexed from 0 to 9. The hash function is indexes take the key, so that's the data, and do modulus arithmetic with 10 on that data. So I'll help you with the first one. The first number we're going to try and store is 14. 14 modulus 10 is 4, so we're going to put the 14 in index 4 in the table. Okay, at this point, I want you to pause the video and just work through the other numbers, and then we'll check the answer in a second. Hopefully you paused, you've come back. Here is the answer. Hopefully that's what you've got. If you got something different, then have a look and see why it's different and make sure that you're on the same page. Right, so now we've got our hash table, we've put all our data or our keys inside the hash table. How would we check if the number we wanted was actually stored in the table? Okay. Well, actually it's quite easy. If I want to check if 14 is in the table, I just take what my hash function is, 14, gives me 4, look at index 4 and check if that's 14. It's there, so I can say, great, 14 is in the hash table. Imagine it was 34 that I was looking for. Again, I do my hash functions, modulus arithmetic, remember? So 34 gives me 4. Look at location 4, check, and it's actually 14. It's not 34, therefore I return false, and it's not in my table. Does that make sense? When a hash function guarantees that no two keys, and remember keys and bits of data, it's interchangeable words, will generate the same index, the resulting hash table is what we call directly addressed. The previous example for the data given was directly addressed because every single bit of data went into the hash table, there was no clashes, no problems. That is a directly addressed hash table. Okay. In reality, the world is not quite that perfect. Typically, the number of entries in a hash table is small relative to the universe of potential keys. Consequently, most hash functions map some keys to the same position in the table. When two keys map to the same position, they collide. A good hash function minimizes collisions. Okay. As an example, back to our previous one, we had our perfectly directly addressed hash table, but what if we want to add some more data in? What do we want to do? What would happen if we add in 23, 49 and 3? So let's just try 23. Okay, 23 modulus 10 is 3, and I've already got something in that box. I've already got 13 in there. I don't want to take the 13 out because I'm still storing that data. So what do I do? I'm going to pause there and let you discuss potential things you could do. And then we'll talk about one example, which is something called a chained hash table, and that's a bit of a clue. So pause there and come back. Okay, so one thing you can do is a chained hash table. A chained hash table fundamentally consists of an array of vectors. So that's a fixed length data structure of say 10, but every single element in that array is actually itself a vector, which is a variable length and can grow as required. The way we think about this is that each vector provides a bucket in which we place all elements that hash to that index. So as an example, we saw a minute ago, what would we do if we wanted to add 23, 3 and 49? Well, we just stretch it down. So now in location 3, we've got 13, 23 and 3 all stored there, and I just have to look to the end of my vector anytime I'm looking for anything in location 3. So imagine I'm looking for number 23. Well, I do my hash function again. 23 modulus 10 is 3. Look at index 3. The first thing I see is 13. I look to see if the chain carries on. It does. Next thing's 23, and then I've returned true, I've got that thing. What if I was looking for 63? Well, I was looking for 63. I would do my modulus arithmetic with 10 again. I look and say, okay, it's going to be index 3. First thing I see is 13, but I can see the vector still carrying on. 23 I see, the vector's carrying on. 3 I see, and then I realise there's nothing after that. The vector's finished, it's of length 3. So 63 does not exist within this hash table. And that's how chained hash tables work. So chained hash tables have a really simple way of resolving collisions. Elements are simply placed in buckets, and those buckets just grow to the size that's required. However, if a lot of collisions happen at one index and the boxes become longer and longer, so accident elements can take more and more time. Ideally, we'd like all the buckets to grow about the same rate. So we'd like to fill everybody once and then everything twice and have a really uniform hash table. And that is actually called uniform hashing for exactly that reason. So if it grows nicely and it grows in a uniform way, it's called uniform hashing, and that requires a uniform hash function. In general, hash tables are only as good as the hash function. The goal of a good hash function is to approximate uniform hashing. You can never ensure uniform hashing unless you know ahead of time exactly the data you're going to be putting in, and then you could actually work it out. But in most cases, the world doesn't work like that. And so what you do instead is try and think about the sorts of data that you might be getting in and think about the sort of hash functions you could have. And then you try and spread the elements through the hash table in quite a uniform manner. So the complexity of chained hash tables, well, you can assert a node in constant time. You can move a node in constant time. You can look up a node in the length of time it takes you to look at every node in that index bucket. So if it's just of sort of width 1 and there's nothing that's gone down on change yet, then it's very, very quick. The longer each of your buckets get, the more you're putting in an index, the slower it gets to work. It's actually time n in the length of the largest bucket. So a really important note, especially as you guys are mainly working in Java, the theoretical data structure sort of definition of a hash table is that you can only store each key once. And if you look in most libraries from most languages, so things like C++, PHP, that is true. That is the way that hash tables work. However, duplicate entries are actually allowed in Java. So it's worth noting that, and it's something you might want to consider when you're doing your programming. So, challenge question. You have a hash table of length 6. I want you to come up with a good hash function for hashing 8 strings. So you're trying to get as close to that uniform hashing as you can. Remember, that has to be a way of mapping the string to an integer between 0 and 5. Okay? And here is the data that you've got to try and put into that hash table of length 6 with index 0 to 5. Hope you find that interesting, and I'll be back with you with a new video after you finish this.